you are mostly welcome to academic research. This is the online tutorial for double E GATE students, and in today's video I will show you how to solve previous year GATE question in simplest method. So let us start the first GATE question. I will show you. So this is the electrical machine GATE question. First we will discuss electrical machine, then we will discuss control system engineering, then we will discuss measurement. So step by step we will discuss all subjects. So let us discuss first electrical machine subject. So first question is leakage flux in an induction motor is. So this is the four option given: flux that leads, flux that links both stator and rotor windings, flux that links none of the windings, then flux that links the stator winding or the rotor winding, but not both. So answer D the correct answer. So the question is, you should understand what is called a leakage flux. There are two types of flux developed in an induction motor. One is called useful flux, another is called leakage flux. Useful flux means the flux that links both rotor and stator winding, but leakage flux means the flux that either develop in the stator or rotor winding, but they are not linked with both the winding. So as they are not linked with both the winding, therefore that flux is called leakage flux. That is, due to that the loss occurs in the machine. Therefore that is called leakage flux. Therefore the answer is D. That is the most suitable answer. That is flux that links with the stator winding or the rotor winding, but not both. So either it is linked with stator winding or rotor winding, but at a time or simultaneously it is not linked with the both the winding. Therefore the loss occurs. Therefore it is called leakage flux. So answer D is the correct answer. So let us see. So question number 2, the angle D in swing equation of a synchronous generator is the angle between stator voltage and the current, the angular displacement of the rotor with respect to the stator, then C is angular displacement of the stator MF respect to synchronously rotating axis. So next is the angular displacement of an axis fixed to the rotor with respect to a synchronously rotating axis. So answer D is the most suitable answer because the angle D in the swing equation of a synchronous generator. So let us see what is called angle D and what is the swing equation. So already we know that swing means, that is, let us consider the synchronous generator. So let us consider the synchronous generator is um, running in steady state, that is supplying a constant load. Suppose now we will increase the load or we can decrease the load in this period, that is called your transient period. That is, let us see, let us take one example. One generator is supplying uh, one area. So let us assume that the load is constant. Suppose suddenly the load increases or decreases, then what happens in case of synchronous generator? Already we know that the synchronous machine either rotates in the synchronous speed or not at all rotate. It means the speed of the synchronous machine is always constant. Uh, so, um, what happens when load increases or decreases? So, generally, when load increases or decreases, then the rotor field axis gradually falls backward, or it lagging behind the uh, synchronously rotating axis, that is your synchronously rotating magnetic field. So let us see the figure. So this is in case of there is no load, or in case of light load, this is the synchronously rotating magnetic field, and this is the uh, rotor rotor magnetic field axis. So now it is coinciding with each other. When there is no load or there is light load condition, there is coinciding with each other. So there is ideally the angle, that is the swing angle is 0 here. But when suddenly load changes, then the synchronously, already we know that the synchronously rotating magnetic field, always it is rotates in a constant speed, that is yours in synchronous speed. This is always, this axis is always remains constant, but rotor magnetic field axis, it falls backward when load increases. This is happens during the transient condition. Therefore, the rotor field axis swings or oscillate back and forward during transient condition when load changes. Therefore, so answer D, the most suitable answer, that is angular displacement of an axis fixed to the rotor with respect to a synchronously rotating axis. So, therefore, angle D in the swing equation of a synchronous generator, the answer D is the correct answer. So, let us see the next question. A single phase transformer has no load loss of 64 watt as obtained from an open circuit test. When a short circuit test is performed on it with 90% of the rated current flowing, its both LV and that is your low voltage and high voltage winding, he measured a loss is 81 watt. The transformer has maximum efficiency when operated at uh, first. We should understand what is your actual question. So this is the question of a single phase transformer has no load loss, that is iron loss. No load means Already we know that from open circuit test or no load test, the loss, that is the wattmeter reading, is nothing but your no load loss, or that is called core loss, or that is your iron loss, as obtained from an open circuit test. Then from short circuit test we can find out the copper loss, because in case of short circuit test, we are supplying, that is the rated current. When short circuit test is performed on it with 90% of the rated current flowing in its both LV and HV winding, is measured loss is, sorry, this is, there is some printing mistake is there. This is the, not he, the measured loss is 81 watt. So the, in case of short circuit test, we are getting the copper loss, that is your 81 watt. Then the question is, the transformer has maximum efficiency when operated at how much percent of rated current? It means in how much percent of rated current. So we are getting the maximum efficiency that we have to calculate. So if we'll understand the question, uh, that is your detailed question, it means if you understand the question bit by bit, then you can find out the solution easily. So it is very important first to understand the question. So let us find out the solution, that is, already we know that, so W naught, that is no load loss or iron loss, also we can denote by Wi. This is also denoted by Wi or W naught, that is your 64 watt, and copper loss is 81 watt. This is already given in the question. So copper loss we are getting at 90% of the rated current. So WCU at 90% is equal to 81 watt. So we now will find out what is the copper loss at any load, that is your X load. X load means that you should understand here. This is very important. So iron loss is always constant. In a transformer, the core loss or iron loss is independent of load condition. That is, either it is half load or full load or quarter load or any fractional load, the iron loss is always remains constant. Uh, but copper loss is the variable loss, that is depend upon load condition. Therefore, already we got at 90% of uh, rated current, because the copper loss, that is I square R loss, that is your according to variation of load, the current varies accordingly the copper loss varies, because copper loss is equal to I square R loss, that is according to load the current varies, so copper loss also varies. Therefore, WCU, copper loss at 90% of rated current, is 81 watt. But at any load, let us assume that that is your X load. So X load means it is maybe half load, half full load or quarter load, that is any load. So WCU for X load is equal to WCU at full load into Ix by IFL. This is your that is current into X. Sorry, Ix is the current at X load, and IFL is the full load current. So this is the formula to getting the copper loss at any load or X load. So WCU at full load into Ix by IFL square. So WCU, now we can find out what is the copper loss at full load. So copper loss at full load is equal to current at full load by current at any load the whole square into WCU for X load. So here uh, WCU for at full load is equal to that is your 81 uh, into here we have taken 81 is the X load. X load means that 90% of the rated current, that is your X load we have considered here. So IFL by IX square into WCU for X load. Therefore 81 WCU for X load we have taken at 90% of rated current, that is your 81 into 1 full load current. Let us assume that is equal to 1, then X load, X is the 90%, so 0.9 into 0.9, that is 0.9 square. So 1 loss square divided by 0.9 loss square into 81. So WCU full load is equal to 100 watt. So we have got the full load copper loss, that is your 100 watt. So now Wi is equal to iron loss at all load, because the iron loss is always constant, and X square WCU copper loss at any load. So mm, because already we know that the copper loss is the I square R loss, therefore according to current variation, so X square any load means we have taken X square WCU, that is copper loss at any load. So for maximum efficiency, copper loss is equal to iron loss is equal to 64. This is the condition for maximum efficiency. Therefore, X square WC is equal to 64. So X we have calculate 80%. Therefore, 80% of rated current, we can find out the maximum efficiency. That is maximum efficiency of us at 80% of the rated current. Therefore, the correct answer is C, that is your 80% of the rated current. So let us see the next. So a 4-pole induction motor supplied by a slightly unbalanced 3-phase 50 Hz source is rotating at 1440 rpm. The electrical frequency in hertz of the induced negative sequence current in the rotor is this is the three four possible answers. So here you should understand the actual question. So a 4-pole induction motor supplied by a slightly unbalanced 3-phase 50 Hz source is rotating at 1440 rpm. The electrical frequency in the hertz of the induced negative sequence current in the rotor. It means, so let us assume that how the when the sequence that is uh, sequence changes, when we will change the sequence, that is phase sequence, that is your R phase, Y phase, suppose RYB, suppose when the phase sequence is changes, there are so many causes for changing the phase sequence. So due to unbalanced load, the phase sequence also changes. So question is asking, if the phase sequence is changes, then what happens to change in frequency? Frequency, how the frequency changes. So this is a very interesting question. So let us find out the solution. So, but this is very simple. That is only you have to remember the formula for negative sequence current frequency. So here given f is equal to 50 hertz and the speed is 1440 rpm. Number of pole is 4. Then synchronous speed we can easily calculate 120 f by p, that is 120 into f 50 divided by 4, number of pole, that is 1500 rpm. So we can easily calculate the slip here, that is slip is equal to ns minus n, that is 1500 minus 1440 divided by 1500, that is ns minus n divided by ns, that is 0.04. So therefore this is the formula to get the negative sequence current frequency, that is f negative is equal to 2 minus s into f. F is the supply frequency, that is 2 minus 0.04 into 50, that is 98 hertz. So this formula you have to remember. This is very simple question, that is your direct question. So let us, the following arrangement consists of an ideal transformer and an attenuator which attenuates by a factor of 0.8. An AC voltage VWX1 is equal to 100 volt is applied across WX to get an open circuit voltage VYZ1 across YZ. Next, an AC voltage VYZ2 100 volt is applied across YZ to get an open circuit voltage VWX2 across WX. Then VYZ1 by VWX1, VWX2 by VYZ2 are respectively what? So you can see the answer here. So this is the question given. So this is the transformer. This is the supply terminal, that is WX, and this is the attenuator, that is here we can see the solution figure. So here we have supplied VWX, then here we are getting output voltage is V, then we have connected, we are taking the output voltage through a tapping, that is your YZ. So this is called your attenuator. It means according to our requirement we can tap the voltage from the output. So this is denoted as VYZ. So the turns ratio here given 1 is to 1.25. So this is the possible answer given, that is this is A, B, C, D answer given. So let us see the solution. So V by VWX is equal to 1.25 divided by 1. So already we know that the transformer having the relationship, that is N2 by N1 is equal to V2 by V1. So N2 by N1, here the N2 is 1.25 number of secondary terms, and this is the number of primary terms. N2 by N1 is equal to V2 by V1. So V2 is that is your V, and this is the VWX. This is the V. This is we have taken here V2, and this is your V1 VWX. So V2 by V1, that is V by VWX is equal to N2 by N1 1.25 by 1. So this is equation. Let us consider equation 1, and also Vyz by V is equal to 0.8. That is your the attenuation factor given zero point 0.8. Therefore Vyz by V is equal to 0.8, or Vyz is equal to V multiplied by zero point 0.8. So now what we will do, just we'll uh, divide equation 1 by 2. Just we'll divide equation 1 by 2. Then we'll get this result, Vyz by Vwx is equal to 0.8 into 1.25 is equal to 1. Therefore we can find out this relationship, Vyz is equal to Vwx, and Vwx already given 100 volt. Therefore Vyz, already we get this relation, Vyz is equal to Vwx, or Vyz1 is equal to Vwx1. Therefore Vyz1 by Vwx1 100 by 100, and Vwx2 by Vyz2 100 by 100. Therefore answer, uh, let us see the answer. This is answer C, the correct answer. So 100 by 100 and 100 by 100. So let us see the next question. The sleep of an induction motor normally does not depend upon what? Rotor speed, synchronous speed, shaft or pole loss component. So answer D is the correct answer. This is also a direct question, and this is a very simple question. So already we know that sleep is equal to S is equal to Ns minus N divided by Ns, and Ns is equal to 120 F by P. Therefore it depends upon rotor speed. um, Rotor speed, it depend upon rotor speed, because rotor speed is the N, and synchronous speed Ns. Next, shaft torque, and also it depend upon shaft torque, because already we know that Ns is equal to 120 F by P, and also the slip is related with the torque equation. The slip is related with the torque equation, both the shaft torque and also the rotor torque, that is your gross torque. Therefore, it depends upon torque. So only it does not depend upon core loss component. It is independent of core loss component. Therefore, answer D is the correct answer. Next question we can see a 220 volt 15 kilowatt 100 rpm shunt motor with armature resistance 0.25 has a rated line current of 68 ampere and a rated field current of 2.2 ampere. The change in field flux required to obtain a speed of 1600 rpm while doing a line current of 52.8 ampere and field current of 1.8 ampere. So it means we have to find out what is the uh, change in flux required. It means uh, in first case, I think this is there is some printing mistake. This is 1000 rpm. So in the first uh, case, the motor is running with 1000 rpm with armature resistance 0.25 ohm. So this having during this rotation or this speed, the line current is 68 ampere and field current is 2.2 ampere. So we want to change the speed from 1000 rpm to 1600 rpm. Then another condition given in this 1600 rpm, the line current must be 52.8 ampere and field current is 1.8 ampere. Then what is the change in field flux? So how much flux will be changed when the speed changes from 1000 rpm to 1600 rpm? This is very simple but important question. So you should clearly understand, and this is the simplest method to understand the question. So let us see the solution. Here the voltage given 250 volt and armature resistance given 0.25 and speed in the first case 1000 rpm and line current IL1 68 ampere and shunt field current 2.2 ampere. So let us see this is your shunt motor, this is the shunt field, and this is the line current, and this is the supply voltage, and this is the back EMF developed in the shunt motor. Therefore, IA1 we can easily find out what is IA1. So here IA1 is equal to line current minus ISH, because there are two parallel paths here. One current already we have got ISH already we know, and this current we know line current. So you can easily calculate this current. This is your armature current. Therefore, we can find out IA1. IA1 is equal to 68 minus 2.2, that is 65.8 ampere Then we can calculate back EMF, that is EB1 in the first case, back EMF, that is V minus IA1 RA, because resistance is always constant. Armature resistance cannot vary because assuming the temperature remains constant. So EB1 is equal to 250 minus 65.8 into 0.25, that is 203.55 volt. So now we will consider the second case. The speed becomes 1600 rpm and line current is 52.8 ampere and short field current 1.8 ampere. Therefore, we can find out the armature current in the second case, that is Ia2 is equal to IL2 minus IS2, that is 52.8 minus 1.8, that is 51 ampere. So EB2 we can calculate, that is V minus Ia2 RA, that is your 207.25. So now we can find out, already we know that the relationship EB is equal to, that is your um, n by 5. So EB1 is equal to n1 by I1 and EB2 is equal to n2 by phi2. Therefore, EB2 by EB1 is equal to n1 by n2 into phi1 by phi2. Therefore, we can already got EB2 203.55 divided by 207.25 and N1 1000 by 1600 and phi1 by phi2. Therefore, we can find out the phi2 is equal to phi1. So, percentage reduction in flux, that is phi1 minus phi2 by phi1 into 100. That is phi1 minus phi12 as 0. That is your 0.63651 divided by phi1 into 100, that is 36%. Therefore, correct answer is 36%. That is uh, this. There is some mistake. The there are two. There is some printing mistake is there. So actual answer, that is around 30, that is approximately 36%, that is 36.36%. So this is having another value, this is also having another value. You should not confuse, there is some printing mistake. So a having either A or B having different values, this is also having different value. The both may not be same. Therefore, answer is 36% or 36.36% approximately. So let us see the next question. A 4-point starter is used to start and control the speed of a DC shunt motor with armature resistance control, DC shunt motor with field weakening control, DC series motor, and DC compound motor. So answer is B, the correct answer, that is DC shunt motor with field weakening control, because already we know that the 4-point starter is used to both purposes, that is for starting purpose of the motor and also to control the speed of the motor, because in case of 3-point starter it will try to control the speed, but it will uh, it is possible by flux control method or field control method. That is, we have to decrease the flux. Once we will decrease the flux, then what happens to uh, NVRC, no voltage release coil, will be demagnetized, and the arm, that is starter arm, will go to off position. Therefore, by 3-point starter, it is not possible to control the speed. Only we have to start the motor, that is mainly used for starting purposes. But in case of 4-point starter, the field current is independent of the uh, NVSC current, that is, it is directly connected to the line. In case of 4-point starter, therefore, if we will decrease the flux, then we can control the speed. Therefore, it is only applicable to DC shunt motor with field weakening control. This is the best suitable answer. So answer B is the correct answer. So let us see the next question. A three-phase salient pole synchronous motor is connected to an infinity bus. It is operated at no load and a normal excitation. The field excitation of the motor is first reduced to zero, then increased uh, in the reverse direction gradually. Then the armature current. So there are four options: increase continuously, first decreases and then decreases, first decreases then increases steeply. So answer B is correct. So because this is very simple question, you should understand this. We should analyze this question in this way. That is, see the synchronous uh, motor. So it means the excitation remains constant. The field excitation motor, uh, the field excitation of the motor is first reduced to zero. It means already we know that the back EMF. In case of DC motor, the back EMF depend upon speed of the armature. But in case of synchronous motor, the back EMF only depend upon the field excitation, because here the speed is always remains constant. In case of synchronous motor, the speed is always remains constant. Therefore, the back EMF only depend upon excitation. That is, when the field is excited, the armature or stator conductor cuts the field flux alternately. That is, when the rotor starts rotating, uh, the field flux cut alternately. That is, first by south pole, then by north pole, then by south pole, then by north pole. Like this, it cut alternately by north and south poles. Therefore, one EMF is developed, that is called back EMF, which opposes the supplied voltage like DC motor. But in this case, as the speed remains constant, therefore back EMF only depend upon excitation. Therefore, this is also called excitation voltage. So it means uh, when the field excitation is reduced to zero, the back EMF also reduced to zero, and it means when back EMF zero, so already we know that then the armature current IA is equal to, that is V minus EB by impedance, synchronous impedance ZS. So as EB is zero, therefore uh, first the current increases. This you can find out the solution. IA is equal to V minus EB by ZS, synchronous impedance. So as EB is zero, so therefore IA increases, because here the um, this become zero, and therefore the first current increases, and then at the excitation then increase the reverse direction. Then as the excitation increases, the back EMF also increases, and the back EMF increases. When back EMF increases, automatically it decreases. So first increases, then decreases steeply. Answer B is correct. So this is the definition of back EMF in case of synchronous motor. Next question: a single phase air core transformer feed from a rated sinusoidally supply is operating at no load. The steady state magnetizing current drawn by the transformer from the supply will have the waveform like this. So it means he is asking, then what is the steady state magnetizing current waveform? What is the shape of steady state magnetizing current waveform? This is a very simple question. This is main key point is that this is a air core transformer. This is the key point that you should understand. Air core transformer means air medium, that is also a magnetic medium, but it is having very high reluctance or resistance to the flow of flux. As the reluctance is very high, therefore it tends to prevent the saturation of the flux. It tends to prevent the saturation of the flux. Therefore, all the magnetic lines are not touch with each other. They are uniformly distributed. Therefore, the flux, that is magnetizing current wave, is a perfect sinusoidal wave. Therefore, answer C is the correct answer. So this is the magnetizing air core transformer, and this is the primary winding. This is the primary winding, and this is the secondary winding. So these are the fluxes, and this is the mutual flux. They are not touched with each other. They are uniformly distributed. Therefore, uh, the wave is perfect sine wave. Thank you very much for watching this video.